I'm happy to introduce Mike Thompson. He is a research associate at Naval Postgraduate School. Mike is the lead developer of RESim, reverse engineering platform, which grew out of his work as a member of the competition infrastructure development team for DARPA's Cyber Grand Challenge. He is the lead developer for the Labtainers Cyber Lab exercise platform and for CyberCIEGE educational video game. Mike has decades of experience developing products for software vulnerability analysis, cybersecurity education, and high assurance trusted platforms. Thank you.
Thank you. Good morning. So yeah, I'll be talking about RESim, which is primarily a reverse engineering platform, but it has a lot of applicability towards cyber testing as well. So the original goals of RESim and its primary goals still are to be able to identify and analyze software that executes on embedded systems. We want to be able to reverse engineer and understand the communication protocols that those systems use so that we can interact with them. And we'd like to be able to discover and analyze potential vulnerabilities using tools such as fuzzing, which I'll get into a little later in the presentation. And primarily, we've been using this system for black box testing. That is systems that we don't have the source code for, we don't have documentation, but we still want to understand what's going on. I think that's also applicable to systems that we should know more about. Maybe we paid to have them built, but maybe we don't have the greatest confidence that we actually know what's going on the boxes. The types of systems that we're talking about are systems. It's not just individual pieces of software that we want to test and reverse engineer. It's software that is sometimes sophisticated, is interacting with other software, potentially on other boxes. And so we want to go through and understand what that software is doing without really knowing anything about it. The key to most of what I'm going to have to say, and the key to most of what makes RESim useful, is the simple fact that cyber testing requires instrumentation, right? You got to know something about what's executing on the system. You got to be able to track it, measure it. Things like code coverage, right? If you can't convince yourself that your tests have actually executed all of the program that's there, you're not going to get very far. Anomaly detection needs some kind of instrumentation. Fuzzing, which I'll get to later, requires feedback to tell the fuzzer what code has been executed. And the fact is that particularly on embedded systems, instrumenting software is not always easy and not always without side effects. So we don't do it. Instead of instrumenting software, we instrument the hardware that the software is running on. Well, not actually hardware, it's models of hardware. So we build these high fidelity models of computer hardware, and that's easy to instrument. And then the idea is we want to run the target software on that modeled hardware. So to do this, we use a full system simulator, something that has such fidelity that I can go into an embedded system, suck the software off of it, grab the chips or whatever, and bring it into the simulator and actually run that software. So we're not talking about things like virtual machines that you're familiar with or QEMU, but complete digital twins of the system. So the idea is you have multiple simulated computers, those boot up and interact with the target software just like the software interacts with real hardware. And again, the hardware that I'm talking about and will be talking about is simulated. So if you think about the memory, if you think about the registers on the processors, those are models of registers on processors. Okay, it's truly a modeled simulation. Now, if you have such a simulated system, you can do some pretty cool things, right? You have the simulation, you can pause it at any time, you can inspect what's going on, you can step forward, you can even go backwards, and everything is moving in lockstep. You don't have to worry about time discontinuities and things like that. And most important of all, you can liberally instrument that simulated hardware so you can figure out what the heck's going on those boxes. Because again, remember, we don't understand what the software is doing, and that's what we're trying to do. So to do this, there's actually a product that is able to do this kind of simulation. It's called Simics. It's a commercial product, been around a long time, and it was originally developed for use by chip vendors. You know, companies that go out and build chips and have firmware that run those chips. Well, it turns out it's pretty expensive and time consuming to build those chips. You don't want to have to go through and fab the chip and do all the testing. And so they spent a lot of effort to build these simulators so that they can model the chips that they're going to build with high fidelity and then test their chips and the firmware before they actually go to fab. More recently, other uses for this product have been DevOps for software developers because it has such great debugging and shared resource capabilities. But until our use of it, there really wasn't any publicly described use as a reverse engineering platform. Primarily, this product has been used for testing known software. Our challenge was to use it to test unknown software. So what we end up with is a picture like this. Up at the top, those are the applications and the Linux kernels that run on the real target system. We've extracted the software from the target system and it's running, but it's running on models of hardware, x86 hardware, ARM hardware, etc. And the Simics product that's managing the simulation is called Hindsight. So it's interacting with all of these models and controlling the simulation. And our product then is interacting with Hindsight in order to figure out what is going on top of the hardware. So I like to think about it as a view of the system from the other side of the hardware, right? We're not looking inside, we're looking from outside. Similar to the virtual machine introspection problem that some of you might be familiar with, but we're dealing with live systems. So how do we do that sort of introspection? So think about on the left side here is the simulator that's creating the models and managing the models on the left here. So I got a model of RAM, say, it's got addresses in the RAM's address space, and I got a model of a CPU. On the right side, I've got the actual execution of the applications that I'm dealing with, right? This model has got high enough fidelity that can take that software and actually run it on that execution environment. If I look at the memory here from this side, and I know it's a Linux system, I know something about the Linux kernel being in memory up towards the high end of memory there. All right, I won't bore you with all the details of the kernel, but I know it's going to be up in there. And also I'm going to know that there is a particular memory location that is going to be hit in the kernel every time some application makes a system call into the kernel. It's always going to go into that same place. And there's going to be a memory location that gets returned out to user space from the kernel. That's always going to be the case. It's not always going to be the same memory location, but it's easy to find. And then the last one I'll bore you with is a pointer to the current task. That is, there's going to be a memory location that's in the kernel that's always pointing to where the current task is. With Simics, I can put triggers or breakpoints on those memory locations, and I can cause a script to run every time somebody, say, executes that particular address, or reads from that particular address, or writes from that particular address. So I can associate callbacks with that. And I can also do things like associate a callback with a transition from user space to kernel space. I can say I want to see that when that happens. So I could use that, for example, in order to figure out where the syscall entry is, right? I just came into the kernel. Well, I must came in from somewhere. Where am I now? So I can answer that question. So how do you take that bit of information and then derive all the information you need about what it is the application's doing? Because that's our goal. Well, in comes DARPA with their deep pockets and their Cyber Grand Challenge. So the Cyber Grand Challenge, I'll take a diversion here a bit to tell you a bit about what this was. The Cyber Grand Challenge was a DEF CON style head-to-head capture the flag competition. So this is a competition that hackers play in which each team gets a computer on a network, right? You get a computer, you get a computer, you get a computer, and I'm the organizer. I give you each services that you got to run on your computers, but they're vulnerable services, right? I put bugs in them. So you got to run your service, you got to run your services, you got to run your services. And so in order to win, you got to figure out where the bugs are in the service, patch it so that you don't get attacked, and then use that knowledge to attack the other teams. So this is a competition, capture the flag, that's played a lot by a lot of different people. But one of the higher level games is at DEF CON in Vegas every year. And what DARPA did, the twist they put on is said, okay, instead of hacker teams doing this, let's have autonomous computers play this game. So that's what the Cyber Grand Challenge was. And the final event was actually at DEF CON in 2016, and it was hosted on DARPA infrastructure. So the government gave away millions of dollars in prize money for this. And so there was a bit of a nervousness about people potentially hacking that infrastructure. I was fortunate enough to be on the competition infrastructure development team, and one of our main jobs was ensuring the integrity of the underlying infrastructure, make sure that we had an argument to say why we believe nobody hacked it. It turns out some people on our team were familiar with Simics from other environments, not public environments, and its use for reverse engineering. And we actually considered running the whole competition on a simulation. This is how paranoid the team became. They said, well, maybe we can just instrument the hell out of this Simic system and run it there, so then we know that if somebody's trying to attack it. Turns out that's not practical for a number of reasons. But what we did decide to do was use Simics during the competition. We had dozens of copies of the Cyber Grand Challenge infrastructure simulated within Simics, instrumented the heck out of it, and took all the competitor-supplied software and vetted it through there to confirm that they weren't trying to attack the infrastructure. So that Cyber Grand Challenge code base was the big head start that we got in developing this RESim product. So the result of all this work is we can do full system execution tracing, again, from the other side of the hardware, tell you all the system calls that are made, dereference all of their parameters. We can use all that information to identify what processes are running in the system, what network connections are being made, what kind of inter-process communication is taking place. We can drill down into individual processes and use plugins on tools like IDA Pro and Ghidra, their disassembler debuggers. And we can use those to interact with the execution in order to set breakpoints to run forward or run backwards. This ability to run backwards is really something quite phenomenal. If you've done software development at low level, you've dealt with things like system crashes and memory corruption, and you want to figure out what's causing the corruption, well, it's really nice to be able to go from the point where you know there's corruption, set a breakpoint on the place where the corruption occurred, and run backwards. And now you're there, and you can see where it came. And with this tool, you can trace the data all the way back to where it came in. We can track ingested data and watch it as it goes through different memory transactions. And we can reverse track data in order to watch and see where selected data has come from. We have integrated the product with the AFL fuzzer that lets us do vulnerability analysis. And with that approach, we are able to directly inject data into the application or kernel memory. And I'll be talking about that more now. Fuzzing might be new to some of you. So just a brief introduction to what it is. It's an extremely commonly used testing technique for software now, in which you essentially take semi-random data, feed it to the program, and see if the program breaks. So think about a program, an arbitrary program is going to maybe read some data, parse the data, and do stuff with the data. So the idea is there something going on in the program that if I misshape the data, or if the data isn't what's expected, is it going to somehow break the program in a way that might cause or might result in a vulnerability? So what the fuzzer does is it generates some random data, sends it to the program, and instruments the program so it knows what it's executing and knows if it crashes. It takes that coverage data and crashes back, figures out what it's going to do the next time, and it just iterates through that thousands of times a minute or as fast as it can. And again, what it's looking for is vulnerabilities, and this is the primary way that vulnerabilities are found in the real world. In fuzzing on real systems, as opposed to a lot of the toys that fuzzers tell you about or academics use, real systems get complicated, right? You've got systems of systems, you've got multi-threaded applications, you've got programs that have got to do a lot of processing before they get to the point where they can be fuzzed, before they're ready to ingest data that you want to potentially corrupt the program with. And so that's often very, very difficult. With a simulated system like RESim and Simics, you can avoid a lot of that harnessing problem, which is done by simply running our system to the point that it's ingesting the data and then pause it, right? Create a snapshot right there. Say, okay, I know I've just read from the network and here's where I want to be to fuzz the data. So I create a snapshot at that point, and like right after a receive call, for example. I can then go through and instrument the heck out of all the basic blocks so I know what code coverage I get. And then I can inject the fuzz data directly into memory. This avoids all kinds of problems about putting the data on a network or into a file and trying to harness and manage the application that's running. I then can unpause the simulation, watch what happens, gather up the instrumentation, feed that back to the fuzzer, and repeat. So one of the real challenges with fuzzing and testing is this notion of code coverage, right? I've got to be able to execute a part of a program if I'm going to test that part of the program. And again, since I'm dealing with software that I don't necessarily understand, it can be a real challenge to get down to different parts of the program. So with our system, we're able to gather up all of the data from the AFL fuzzing and find branches that weren't taken, places where we got to a place in the code and we always went one way, but not the other. And so we're able to bring up those places for the analyst and have the analyst determine if some input data could have led to a branch that wasn't led to. And what that looks like, I don't want to bore you with the details of the assembly language, but the green code, it represents code that was actually executed through one of the fuzzing sections, where the blue represents code blocks that were never hit for whatever reason. So with the system, we can quickly come up and say, okay, I want to get here so that I can look at the data and try and figure out manually why the heck I never got here, right? Because maybe here leads to a whole bunch of other blocks that do interesting stuff. So if I can figure out how to get down there, I'm suddenly have testing that's more meaningful, right? So that's a big part of what we're doing with the system is providing that feedback for the analyst, put the analyst in the loop, and that gets us better fuzzing and better test coverage. So we've been using this product since I'm at the Navy School. We've been using it to reverse engineer commercial maritime systems, the kind of systems you might find on the bridges of commercial vessels or military vessels. So we've used it to analyze the protocols, functions, put together concept of operations on the devices, and we've identified several vulnerabilities within some of the network services. We've had several master's students use the product in their theses. Last year, an OSD panel judged RESim as the best RFI response in the field of next generation simulation. And last week, U.S. Cybercom had their inaugural Cyber Recon program, which is a university program that they put together for cyber research. And one of my thesis students took the top place for offensive cyber research tools. Okay, so summarize what we found is cyber testing requires instrumentation. And if you try to instrument modeled systems, that can actually work. It's viable. So you can actually take the, the models of the hardware, instrument them, and figure out what the software is doing and watch it and use that for testing. As I noted, it can greatly simplify fuzzing. Fuzzing can be extremely difficult on real systems and embedded complicated systems. This makes that much easier. And your developmental testing, if you think about developmental testing and evaluation, it can greatly simplify that as well because of this ability to pause and reverse. The other thing I want to point out is that the hardware models need not be perfect, right? I kind of glossed over. I said, oh, we've got these magical models that are high fidelity and represent the system. Well, in a lot of real systems, they require peripheral units or specialized hardware that maybe you don't have a model for, and maybe you don't have the budget to model it. You know, if you talk to people that are getting into the digital twin world, It all looks well and good until you've got to actually have a digital twin of something that's fairly esoteric. Now, maybe you can model that, and with Simics, you can go and build your own models, but maybe you don't have the budget for it. Something I want to leave with you is that the models need not be perfect. Remember, for our purposes, we're just trying to get the software to run and execute largely as it does in the real world. Of course, the better the fidelity you have, the better you're off, but sometimes you can't have everything. But our experience is that even fairly generic models of, say, an ARM-based platform can get you a really long way towards testing a lot of this complex software. So this Simics product, this magical Simics product, doesn't require supercomputers to run. It runs on commodity hardware, servers, engineering workstations. And it's expensive, very expensive, except Intel has offered a free version of the Simics product that models x86 platforms. So you can go and get it now and use it. They have a very liberal license agreement. Unless you're developing products, you're pretty free to use it. So you can use that with our RESim product, which is on GitHub. And also on there is our IDA Pro and Ghidra plugins. So you can actually run this stuff and try it out yourself. Currently, we run Analyze Linux on x86 and ARM. We, of course, would like to expand that to include other operating systems like VxWorks. And we've actually started some work on Windows. And that's what I got. Any questions? Yes.
So to what degree does the software allow you to simulate various physical effects? So can you look at row hammer type things, or if you have something that's trying to do a side channel with like power calculations or something of that sort, are you able to model with enough fidelity to be able to execute software?
I've not actually worked at that. I've done some work with their models, and their models are very open. You can even like write C programs to affect the models. So I expect you could do that. It's not part of this, not part of the RESim product, but I think the Simics product could be used towards that end if you've got a model in mind of what row hammer would look like. Yeah.
So at DEF CON 25, there was a presentation on sort of the undocumented calls within the x86 processor family. Is that a problem that has actually ever occurred in the real world? Is that very hypothetical? Does this show up in Simics at all?
So I'm not an expert in that realm, but I know people are very concerned about it. In fact, when we started using Simics for the Cyber Grand Challenge, our DARPA program manager actually contracted with Intel so that we could use their better x86 model, not the one that they gave to Wind River to sell. So we had a higher fidelity one that they were assuring us met the, I don't know the right words, but met the mask, maybe.
Thank you.
One back here. Flip the switch.
Hello. There we go. You mentioned that this could model, or this could be used on really complex systems. So I was wondering about the scope of the applications that you can apply this to. And also you're getting really granular in how you're instrumenting this. What's the workload on your end or on the instrumentation side to set this all up?
So the workload was figuring out how to make all this work. Now it's relatively straightforward, and the system automates all of that. So the workflow is you bring me an embedded system. I take the software off of it, figure out what the kernel is, take the kernel, run it through our algorithms that tell us the handful of addresses that we need to pick out of that. And that's all automated. And then we start running the application. That's all automated. Watching the system calls, producing a full system trace. And then it's a matter of the analyst, right? You need a reverse engineer that's going to look at the process traces and say, oh, well, that's an interesting process because he attaches to this UDP port and it looks like he reads some data off of there. Let me go through the process of shaping some data, feeding it through there and watching what happens and tracking it and whatnot. Did that answer your question?
Yeah. So you mentioned the ship example.
Yeah.
So how long? What was that whole end-to-end iterative process like? How long did that take?
I would say a couple of man months in order to take a fairly complex maritime system or embedded system that's used anywhere, and run it through enough where you've gone through and you've identified interesting processes and begun to fuzz them. Yeah. Mm-hmm. Yes.
Yeah, so on the fuzzing side of things, that's the next dimensional problem we have all the executions of the program.
Yes.
Does RESim have any secret sauce to mitigate that cost?
The secret sauce is the person, right? So you give it to AFL, and AFL it can only go so far with randomness, right? If there's a string that the program's looking for, AFL is never going to guess the string, and human can maybe quickly do that. And finding things like, oh, it looks like there's a checksum there, right? I'm looking at the code, and so that's real easy for the human to come up and see that little checksum loop, and of course I'd like to automate that as well. I mean, I've looked at enough of these checksum loops I ought to be able to have a program that says, oh, that's a checksum loop. Let me bring that to the analyst's attention and fix it. But yeah, it's getting through all those different paths, but that's the rub, right? If you're not executing it, you're not testing it.
Well, as the session chair, I'll take the last question then. So you discussed a lot about vulnerability analysis, looking for issues in embedded systems. Have you done any work for maybe malware forensics, right? So imagine you have some piece of unknown code that's doing things. Have you used RESim for that purpose?
I have not. I've not used Simics for that, but I know people do, and I know it's a great platform for that for all the reasons I described. You can pause the execution, you can step forward, you can inject your own data. It gives you maximum visibility without interfering with what's going on. You don't have to run any of your own software on the target system, no shells, anything like that.
Great. Well, everyone, let's thank Mike again.